Let us continue our discussion on the general theory of shells and the membrane theory of shells for application to cylindrical shell structures that are commonly implemented in the industry. To refresh your memory on the discussion till this point, recall that the general state of internal actions in a general shell element, that is a differential shell element with differential dimensions dx and dy, comprises of four unknown membrane actions or in-plane actions that are Nx and y, the two in-plane or membrane axial forces, and Nxy and Nyx that are the two in-plane or membrane shear forces, in addition to the six unknown internal plate actions or unknown internal out of plane actions that are the bending moments Mx, My, and the associated shear forces Qx, Qy, as well as the torsional moments Tx, Ty, all of which act out of the plane of the shell and thus are out of plane internal actions, thus resulting in a total of 10 unknown internal actions, that is 4 unknown internal membrane actions and 6 unknown plate actions just enumerated. The solution of the unknown internal actions, that is the 4 unknown internal in-plane or membrane actions Nx, Ny, Nxy, and Nyx, and the 6 unknown internal plate actions or out of plane internal actions, that is Mx, My, Qx, Qy, Tx and Ty, is to be completed by applying the fundamentals of mechanics and the exercise involving the solution of the unknown internal actions in a general differential shell element based on mechanics is termed as the membrane analysis and plate analysis of the general shell element. Further, as a recap, recall that the number of equations that are available from the consideration of statical equilibrium of the general differential shell element are only 6 that are the 3 force equilibrium equations: sigma fx equal to 0, sigma fy equal to 0, and sigma fz equal to 0, and the 3 moment equilibrium equations, that is sigma mx equal to 0, sigma my equal to 0, and sigma mz equal to 0. Thus resulting in a total of 6 statical equilibrium equations which can be applied to solve for the unknown internal actions in the general differential shell element. However, since there are 10 unknown internal actions that need to be solved, and while there are only 6 equations available from the consideration of statical equilibrium of the general differential shell element, the problem of the solution of the unknown internal actions in a general differential shell element remains statically indeterminate. However, one may recapitulate that the simplifying assumption of thin shells, that is, the simplifying idealization that the shell is thin, reduces the number of unknown internal actions from 10 to only 3 upon the application of the 6 statical equilibrium equations. Rather, 3 statical equilibrium equations, which are the 3 moment equilibrium equations. And the membrane analysis, that is, the analysis of the shell element for the solution of the unknown internal membrane actions, therefore resulted in the 3 unknown remaining in-plane internal membrane actions, which were nx, ny, and one of the two, nxy or nyx, after the application of the 3 moment equilibrium equations. And since the 3 force equilibrium equations are still remaining or remain to be applied, that is, the 3 force equilibrium equations, sigma fx equal to 0, sigma fy equal to 0, and sigma fz equal to 0, are not yet applied or used. We have 3 remaining statical equilibrium equations, which are the 3 force equilibrium equations, to solve for the 3 remaining unknown internal membrane actions, nx, ny, and nxy. It is worthwhile to mention here that The realistic and valid assumption of thin shells, that is the assumption that the shell in the differential general shell element is a thin shell, provided the shell satisfies the necessary and sufficient mathematical condition given by equation 1 presented in one of the earlier slides to qualify as a thin shell. The flexural rigidity or the bending stiffness of the shell being negligible on account of being a thin shell, the shell is unable to resist any out of plane or plate actions. In particular, a thin shell that qualifies the necessary or sufficient mathematical condition given by equation 1 presented in the previous slides for being a thin shell is unable to resist the out of plane bending moments and out of plane torsional moments, that is mx, my, tx and ty, due to the negligible flexural rigidity or bending stiffness of the thin shell. As a result, the out of plane bending moments mx, my and out of plane torsional moments tx and ty in a thin shell are themselves negligible or have to vanish by the virtue of the thin shell assumption, because of which the thin shell is unable to resist any out of plane bending moments or torsional moments. As a consequence, the external loads on the general differential shell element, that is a thin shell, have to be resisted by in-plane or membrane actions only. A hypothesis that was proven to be the membrane theory of thin shells, which states that the external loads or the externally applied forces acting on a thin shell that qualifies the necessary and sufficient mathematical condition stated by equation number 1 presented in the previous slide to qualify as a thin shell are resisted only by in-plane or membrane actions, since the negligible flexural rigidity or negligible bending stiffness of a thin shell reduces or diminishes the out of plane bending moments and the out of plane torsional moments resisted by the thin shell to a negligible value. And since the outer plane bending moments mx, my and the outer plane torsional moments tx and ty that are resisted by a thin shell are negligible or reduced or diminished to zero, the application of the three moment equilibrium equations, that is sigma mx equal to 0, sigma my equal to 0, and sigma mz equal to 0, reduces the number of unknown internal actions in the general differential shell element, that is a thin shell element, from 10 to only 3, which are nx, ny, and nxy, as the other actions, that is the outer plane or plate actions mx, my, tx, ty, and qx, qy, all vanish as demonstrated mathematically or proven mathematically by the application of the three moment equilibrium equations to the thin differential shell element. With that recap or review of the membrane theory of general or differential shell element, that is also a thin differential shell element, we will now converge to the membrane theory or membrane analysis of cylindrical shell structures that are provided with a thin shell, and as suggested by the term membrane analysis, we will apply the remaining statical equilibrium equations, that is the three remaining force equilibrium equations, sigma fx equal to 0, sigma fy equal to 0, and sigma fz equal to 0, to the thin shell element for solving the three remaining unknown internal membrane actions nx, ny, and nxy in a thin cylindrical shell element. The theoretical formulation that will be developed based on the application of the remaining statical equilibrium equations, that is the three statical force equilibrium equations, for the membrane analysis of thin cylindrical shells are also referred to as the membrane theory of thin cylindrical shells. In other words, the theoretical formulations that are based on the application of the statical force equilibrium equations for the solution of the unknown internal in-plane or membrane actions Nx, Ny, and Nyx or Nxy in a thin cylindrical shell element based on mechanics constitute the membrane theory of thin cylindrical shells, and the membrane theory of thin cylindrical shells can be summarized or stated in a nutshell by the statement that the externally applied loads or forces acting on a thin cylindrical shell element are resisted primarily or predominantly by the internal in-plane or membrane actions Nx, Ny, and Nxy only. However, in case of a cylindrical shell structure, the membrane analysis of a thin cylindrical shell or thin cylindrical shells in general, based on the membrane theory of thin shells, for the purpose of solving for the unknown internal membrane or the in-plane actions under the actions of the external forces or external loads Px, Py, and Pz, is performed more conveniently by formulating the equations, that is the statical equilibrium equations, with reference to a cylindrical coordinate system. Due to the characteristic geometry of a cylindrical shell, which intuitively suggests a choice of the cylindrical coordinate system as the most convenient frame of reference for simplicity and convenience in the formulation of the equations of mechanics that are required for the solution of the remaining unknown internal in-plane or membrane actions induced by the external loads Px, Py and Pz on the thin shell element. Therefore, selecting the choice of cylindrical coordinate system as the convenient frame of reference for the membrane analysis of a thin cylindrical shell with the radial axis R aligned along the radius of the cylindrical shell, the longitudinal axis X of the cylindrical coordinate system aligned along the longitudinal axis of the cylindrical shell, and the tangential or the circumferential axis theta of the cylindrical coordinate system aligned along the circumferential direction of the cylindrical shell. Let us formulate the necessary equations of mechanics for the thin cylindrical shell in this cylindrical shell structure with a thin shell based on the considerations of the statical equilibrium of a differential thin cylindrical shell element that is highlighted as the dashed square on the surface of the cylindrical shell structure and is illustrated on the right hand side figure with the various internal in-plane membrane actions or in-plane unknown internal actions that are induced by the externally applied loads or forces Px, Pr and P theta. Applied along the three coordinate directions of the selected cylindrical coordinate system. As one can note from the figure on the left hand side presented on the slide, the differential shell element in the cylindrical shell structure with a thin shell is identified by the shell element represented by the dashed or shaded region that is bounded by the planes x and x plus dx and the planes theta and theta plus d theta along the two cylindrical coordinate axes x and theta, and magnified or enlarged view of the differential shell element in the cylindrical shell structure with a thin shell, that is the enlarged view of the differential thin cylindrical shell element highlighted by the shaded region is shown on the right hand side of the present slide as a differential shell element of a thin cylindrical shell subjected to external loads px, pr and p theta acting along the three coordinate directions of the cylindrical coordinate axes x, r and theta that induce the internal actions which are the unknown internal in-plane or membrane actions nx and theta, the two internal in-plane axial forces acting on the x and the theta face of the thin differential cylindrical shell element presented in the figure on the right hand side of the present slide, as well as the internal in-plane or membrane shear forces nx theta and n theta x also shown in the figure, noting that the differential shell element of a thin cylindrical shell that is presented on the figure on the right hand side with the cylindrical shell structure illustrated in the figure on the left hand side of the present slide has differential dimensions, that is the dimension dx along the cylindrical coordinate axis x, the dimension a d theta along the circumferential or tangential cylindrical coordinate axis theta, where A is the radius of the cylindrical shell structure presented in the figure on the left hand side of the present slide, of which the differential shell element is a part. The sign convention for the positive directions of the unknown internal in-plane or membrane actions nx, n theta, and nx theta and n theta x are the same as the sign convention that was adopted for defining the positive directions of the in-plane internal actions or the unknown internal in-plane or membrane actions nx and y, nxy and nyx in case of the general differential shell element. Considered with reference to the Cartesian coordinate system as discussed earlier. Hence, the differential cylindrical shell element that is a differential element in a cylindrical shell structure with a thin shell represented by the shaded region is in equilibrium under the action of the externally applied loads or forces Px, Pr, P theta acting along the three cylindrical coordinate directions x, r and theta, as well as the unknown internal in-plane or membrane actions nx and theta, nx theta and n theta x it is worthwhile to mention here that since the sign convention and the notation that has been adopted for representing the internal actions and the external forces is based on the premise that the internal actions are defined or measured per unit length, while the external forces or external loads are defined or specified per unit area. The differential thin cylindrical shell element illustrated on the figure on the right hand side of the present slide is in statical equilibrium under the action of the externally applied loads or forces. For example, Px, Pr and P theta along the three coordinate directions x, r and theta, each of which multiplied by the area of the surface area of the differential shell element, that is a d theta dx, to arrive at the externally applied forces, while the internal actions, that is the internal inner plane or membrane actions that are to be solved for example, nx, n theta, nx theta, and n theta x, have to be multiplied by the length of the surface on which they act, respectively, to arrive at the forces or the forces alternates of the internal actions nx, n theta, nx theta, and n theta x. In other words, the unknown internal actions, that is the unknown internal in-plane or membrane actions nx, n theta, nx theta, and n theta x, are specified per unit length, while the external forces or externally applied loads Px, Pr, and P theta acting along the three cylindrical coordinate directions x, r, and theta are specified per unit area and are therefore area loads. Proceeding with the membrane analysis of a thin cylindrical differential shell element that was presented in the previous slide, for the membrane solution of a thin cylindrical shell, for the purposes of obtaining the solution of the unknown internal in-plane or membrane actions in the thin cylindrical shell element, noting that the thin cylindrical shell element that qualifies the necessary and sufficient mathematical condition for a thin shell in case of a cylindrical shell, that is, the thickness of the cylindrical shell is much less, then the only finite radius of curvature of the cylindrical shell, A, illustrated in the previous slide as the second radius of curvature R2 in case of a cylindrical shell, is infinity. And also noting that the flexural rigidity or the bending stiffness of a thin cylindrical shell that satisfies the necessary and sufficient condition to qualify as a thin shell in case of a cylindrical shell structure, as expressed by this inequality, is negligible, the outer plane bending moments mx, m theta, and the outer plane torsional moments tx, t theta have to vanish, since the thin cylindrical shell is unable to resist any outer plane moments. As a consequence, the only remaining or non-zero internal actions that are unknown, or the only remaining unknown variables that need to be solved for, are the in-plane or membrane axial forces nx, n theta, the in-plane or membrane shear forces nx theta and n theta x, and the outer plane shear forces qx and q theta. Further, recognizing that each of these remaining non-zero unknown internal actions, that is nx, n theta, nx theta, n theta x, qx and q theta, that need to be solved for, varies spatially. That is, the remaining non-zero internal actions vary in the spatial directions x and theta in general. We will proceed to apply the remaining or the unused statical equilibrium equations, that is, the statical moment equilibrium equations that have not yet been used or applied, after the application of the thin shell assumption. Recall that the application of the thin shell assumption resulted in the vanishing or diminishing or reduction of the outer plane moments, that is the outer plane bending moments mx, m theta, and the outer plane torsional moments tx theta to zero on account of the negligible flexural rigidity or the negligible bending stiffness of the thin shell, thus resulting in the only 6 remaining or non-zero internal actions, which are nx, n theta, nx theta, n theta x, qx and q theta. Hence, To solve for the remaining non-zero internal actions, we apply the statical moment equilibrium equations that are still remaining to be used, which are sigma mx equal to 0, sigma m theta equal to 0, and sigma mr equal to 0, which are the pertinent or relevant statical moment equilibrium equations with reference to the selected cylindrical coordinate axis as the choice of the frame of reference for purposes of formulating the equations of mechanics for the thin cylindrical differential shell element illustrated in the previous slide. Therefore, applying the remaining statical moment equilibrium equations one by one, beginning with the most obvious and straightforward statical equilibrium equation, that is sigma mx equal to 0, and sigma m theta equal to 0, results in a zero value of the outer plane shear forces q theta and qx that are associated with the bending moments mx and m theta, as the thin cylindrical shell element is unable to resist any outer plane bending moments mx or m theta, which therefore have to vanish, thus resulting in a zero value of the associated outer plane shear forces q theta and qx respectively. The application of the third statical moment equilibrium equation, sigma mr equal to 0, that is the statical moment equilibrium equation for moment equilibrium about the radial or r-axis, results in an equality between the in-plane or membrane shear forces nx theta and n theta x. The inequality can be recognized as a familiar equation, rather the equality. The equality of the in-plane or membrane shear forces nx theta and n theta x resulting from the application of the statical moment equilibrium equation about the radial r-axis can be recognized as the familiar equation that depicts the rotational equilibrium of the differential thin cylindrical shell element illustrated in the previous slide which requires that the in-plane or membrane shear forces nx theta and n theta x should both be equal and opposite to each other, which are therefore termed as complementary shear forces that are necessarily equal and opposite to each other to maintain the rotational equilibrium of the thin differential cylindrical shell element about the radial axis R. Now that we have utilized all the three moment equilibrium equations based on the considerations of statical equilibrium of the thin cylindrical differential shell element illustrated in the previous slide, we have only three remaining unknown internal actions, which are nx, n theta, and n, one of the two, nx theta or n theta x. Let us retain nx theta as the unknown internal membrane shear force, since the determination of nx theta will result in the determination of the complementary unknown internal membrane shear force n theta x by itself. In order to solve for the three remaining unknown internal membrane actions nx and theta and nx theta, we have the three remaining statical force equilibrium equations, that is sigma fx equal to 0, sigma f theta equal to 0, and sigma fr equal to 0, which are yet to be applied or still unused. Recognizing that each of the remaining unknown internal membrane actions nx, nx theta vary spatially, that is, each of the three remaining unknown membrane actions nx, n theta, and nx theta vary in the spatial direction. We will continue the membrane analysis with the application of the three remaining statical force equilibrium equations for the thin cylindrical differential shell element illustrated in the previous slide, as represented by these equations. Considering the force equilibrium of the thin differential cylindrical shell element illustrated in the previous slide in the coordinate direction x of the selected cylindrical coordinate system, one can write the statical force equilibrium equation x in the coordinate direction x as represented by this equation here, cancelling or negating the like terms in the equation. One can obtain the simplified form of the statical force equilibrium equation in the coordinate direction x of the selected cylindrical coordinate system as this equation right here. Noting that the in-plane or membrane shear force n theta x does not vary in the x or r coordinate directions of the cylindrical coordinate system, the partial derivative of the in-plane or membrane shear force n theta x is equal to the full derivative, the statical force equilibrium equation for the thin cylindrical differential shell element in the x coordinate direction may be written in a compact form as this equation. Proceeding to the next statical force equilibrium equation in the coordinate direction theta, that is the tangential or the circumferential coordinate axis theta of the selected cylindrical coordinate system, one can write the statical equilibrium equation for force equilibrium equation for the force equilibrium in the tangential or circumferential direction theta as this, cancelling or negating the like terms or the identical terms which are equal and opposite to each other in sign, and noting that the in-plane or membrane shear force nx theta does not vary in the circumferential direction theta or the radial direction r of the selected cylindrical coordinate system, the partial derivative of the in-plane or membrane shear force nx theta is equal to the full derivative of the in-plane or membrane shear force nx theta. One can express the statical force equilibrium equation for the thin cylindrical differential shell element illustrated in the previous slide by this compact equation. Hence, as a conclusion to the formulation of mechanics presented in the present slide, for the differential cylindrical shell element that is also a thin shell and illustrated in the previous slide, can be summarized by these two equations, which are based on the assumption, that is an additional assumption in addition to the thin shell assumption, that higher order terms of the differential dimensions dx and d theta are negligible, since dx and d theta themselves are tending to zero or are differential quantities. For the values of dx and d theta tending to zero, that is, for the assumption that dx and d theta are differential quantities, the square of the differential quantities dx and d theta, that is dx square and dx theta square, d theta square respectively, are therefore almost equal to 0. And all higher terms of dx and d theta, including dx square and d theta square, are almost equal to 0. Before we proceed with the membrane analysis of thin cylindrical shells based on the membrane theory of thin cylindrical shells, let us reflect and review the status of the membrane solution that we have obtained so far based on the general state of internal actions in a differential general thin cylindrical shell element that was presented in the figure in the previous slide, and assess the status of the determinacy or indeterminacy of the membrane solution that has been achieved thus far after the application of the thin shell assumption. Recall that the application of the thin shell assumption, that is both realistic and valid for cylindrical shells that qualify the necessary and sufficient mathematical condition for a thin cylindrical shell, that is, the thickness of the thin cylindrical shell is much less to the one and only radius of curvature A of the cylindrical shell. The general state of internal actions in the cylindrical shell element was simplified by reducing the number of non-zero or finite unknown variables from 10 to only 6 by the application of the thin shell assumption. It may be worthwhile to note here that the application of the thin shell assumption for the solution of the unknown internal actions in a differential cylindrical shell element displayed in the figure in one of the earlier slides resulted in zero values or negligible values for the out of plane bending moments mx, m theta, as well as the out of plane torsional moments tx, t theta, thus simplifying and reducing the general state of internal actions in the differential cylindrical shell element from 10 unknown internal actions to only 6 remaining unknown internal actions, which are or were found to be the in-plane or membrane actions nx, n theta, nx theta and n theta x, and the two unknown internal outer plane or plate actions qx and q theta. On the application of the moment equilibrium equations based on the consideration of the statical moment equilibrium of the differential thin cylindrical shell element, the unknown internal outer plane shear forces qx and q theta vanished in order to satisfy the moment equilibrium equations sigma mx equal to 0 and sigma m theta equal to 0, while the third moment equilibrium equation sigma mr equal to 0, that is the rotational equilibrium equation for the differential thin cylindrical shell element, required that the two in-plane internal membrane shear forces nx theta and n theta x should be equal and opposite to each other and therefore nullify each other. Physical phenomena which is the standard terminology of mechanics is termed as the rotational equilibrium of the differential shell element that necessitates the equality between the two in-plane membrane shear forces nx theta and n theta x in case of the differential thin cylindrical shell element displayed in the figure on one of the earlier slides, which are therefore termed as complementary shear forces. In conclusion, by inspection of the equations obtained thus far, based on the application of the thin shell assumption, the statical equilibrium of the thin cylindrical shell element presented in the figure in one of the earlier slides resulted in three unknown internal actions which were the unknown internal in-plane axial force nx and theta, and one of the two unknown internal in-plane or membrane shear force nx theta or n theta x. However, the examination, that is, the inspection of the equations derived thus far based on the membrane theory of thin cylindrical shells for a differential thin cylindrical shell element exhibited in the figure on one of the earlier slides, it is apparent that the actual number of unknown variables that remain to be solved, that is, the actual number of unknown internal actions that need to be yet to be solved, are 6 in number, which are the unknown internal in-plane axial forces nx and n theta, and one of the two unknown internal in-plane shear force nx theta or n theta x, since the two are complementary shear forces and therefore equal to each other. And additionally, their variational components, that is, the components that are mathematically represented by the variational terms del by del x or del by del theta, that are presented in the equations obtained thus far after the application of the thin shell assumption, based on the membrane theory of thin cylindrical shells, as the resulting statical equilibrium equations which were presented in the previous slide. In conclusion of the membrane analysis of thin cylindrical shells, in other words, the membrane solution of thin cylindrical shells that has been obtained thus far by the application of the statical equilibrium considerations as well as the thin shell assumption to the differential thin cylindrical shell element exhibited in the figure in one of the earlier slides results in 6 actual number of unknown variables that are nx, n theta, and nx theta, as well as their 3 variational components that are mathematically represented by the variational terms del by del x or del by del theta. Since the variational components of the unknown internal actions represented by the variational terms del by del x or del by del theta in the statical equilibrium equations obtained or derived in the previous slide will result in a differential equation in general, an ordinary differential equation. The interpretation of the statical equilibrium equations that have been derived thus far and presented in the previous slide suggests that the variational terms will constitute or present a differential equation which apparently would be an ordinary differential equation that will need to be integrated, and the integration of the differential equation that is resulting or results from the variational terms del by del x or del by del theta will present additional unknowns in the form of unknown constants of integration, say C1, C2, etc. Hence, contrary to our original expectation that there are only three unknown internal in-plane or membrane actions that remain to be solved after the application of the statical force and moment equilibrium equations and the thin shell assumption to the differential thin cylindrical shell element presented in the figure in one of the earlier slides, the actual number of unknown internal actions, or the actual or total number of unknowns that need to be solved, are actually more than three, since in addition to the unknown internal in-plane or membrane actions nx n theta and nx theta, which yet remain to be solved or yet unsolved, their variational components represented by the variational terms del by del x and del by del theta in the equations derived in the previous slide present additional unknowns which are the constants of integration, say C1, C2, etc., that result from the integration of the differential equations arising due to the variational terms del by del x and del by del theta, as demonstrated or illustrated by the derivation presented in the previous slide. Hence, in conclusion, to the status of the membrane solution of the unknown internal in-plane or membrane actions in a differential thin cylindrical shell element based on the membrane theory of cylindrical shells, and the inherent statical equilibrium considerations, the total number of unknowns, therefore, that yet remain to be solved, including the variational terms del x by del by del x and del by del theta, are 6 in numbers. While the equations that we have derived in the previous slide based on the application of the statical equilibrium, considerations of the differential thin cylindrical shell element, as well as the simplification achieved by the thin shell assumption, are only three. Hence, the problem of the solution, that is the membrane solution of the unknown internal in-plane or membrane actions nx n theta and nx theta with reference to the differential thin cylindrical shell element presented in the figure in one of the earlier slides remains indeterminate simply because of the variational terms del by del x or del by del theta that represent the variational components of the internal in-plane or membrane actions and result in a differential equation, each thus presenting the differential equations derived in the previous slide, each of which will present additional unknowns in the form of unknown constants of integration. For example, C0, C1, and so on. Thus, in conclusion, the membrane solution of the unknown internal in-plane or membrane actions remains statically indeterminate even after the application of the membrane theory based on the statical equilibrium of the differential thin cylindrical shell element as well as the thin shell assumption. Henceforth, to proceed with the solution of the remaining unknown internal in-plane actions nx n theta and nx theta in the differential thin cylindrical shell element presented in the figure in one of the earlier slides, as well as the unknown constants of integration that are presented by the integration of the differential equations resulting from the variational terms del by del x and del by del theta in the statical equilibrium equations presented in the previous slide, which are in general first order ordinary differential equations, and therefore result in an unknown constant of integration. Noting that the solution of the unknown internal in-plane or membrane actions, that is the membrane solution for the differential thin cylindrical shell element, still remains statically indeterminate even after the assumption of the thin shell that is mathematically represented by this inequality in the region of interest or the region of the solid material of the shell. Intuitively, one can interpret or conclude that the membrane solution, that is the solution of the unknown internal in-plane or membrane actions, will require another simplifying assumption in addition to the earlier implemented thin shell assumption. Now, based on engineering judgment, as in case of any engineering problem, the simplifying assumption or the simplifying idealization that is implemented for the solution of the engineering problem should not only be realistic but also valid mathematically and should not result in any significant loss of accuracy in the solution of the engineering problem. A rational and realistic assumption that is mathematically valid and also physically realistic is that the external forces or the external loads, that is the external loading, acting on the cylindrical shell structure of which the differential cylindrical shell element is a part, are axisymmetric. That is, the external loading or external forces are symmetrical with respect to the longitudinal axis of the cylindrical shell structure. The assumption, numbered as assumption number 2 in the present slide, is not only physically realistic but also mathematically valid in case of cylindrical shell structures that are subjected to axisymmetric loading, that is external loading or comprising of external forces that act symmetrically with respect to the longitudinal axis of the cylindrical shell. And in case of such axisymmetrically loaded cylindrical shell structures, assumption number 2, that is the additional assumption in addition to the thin shell assumption that we will be applying to complete the solution of the unknown internal in-plane membrane actions is acceptable provided the cylindrical shell structure is axisymmetrically loaded. That is, the cylindrical shell structure is subjected to only axisymmetric external forces or external loads, which are symmetrical with respect to the longitudinal axis of the cylindrical shell. Mathematically, the assumption number 2, that is the assumption of axisymmetric loading, implies that p theta, that is the tangential or the circumferential load, must be 0. Since the circumferential or tangential load p theta, by its very nature of being a tangential load, violates axisymmetry. It is worthwhile to note here that the assumption of axisymmetric loading on the thin cylindrical shell structure is not too restrictive. In other words, the second assumption of axisymmetrically loaded cylindrical shell is quite general or applicable to most of the cylindrical shell structures that are encountered in the industry, as mentioned in the introduction to the cylindrical shell structure discussed in one of the initial slides. And the reason that the assumption number 2 of axisymmetrically loaded cylindrical shell structure is not too restrictive is that most practical cylindrical shell structures that are implemented in the industry, for example, the cylindrical water tank subjected to hydrostatic loading that can be mathematically represented by the hydrostatic pressure, cylindrical pressure vessels with the uniform internal pressure that can be mathematically represented by a uniform internal pressure as the radial external load, or commonly encountered in the field or the industry. To summarize, the simplifying assumptions or simplifying idealizations that we have implemented or applied for the membrane solution of thin cylindrical shells or cylindrical shell structures in general, based on the membrane theory of thin cylindrical shells, may be mathematically represented or mathematically modeled by these two equations, that is, the thin shell assumption can be mathematically depicted by this inequality, wherein the radial coordinate are in the selected choice of the cylindrical coordinate system of frame of reference for the membrane analysis of the cylindrical shell structure, has a very small range, that is, the radius r or the radial coordinate r of the cylindrical shell structure in case of a thin shell ranges over a very small range, that is from a minus t by 2 to a plus t by 2, where a is the radius to the mid surface of the cylindrical shell structure, t is the thickness of the cylindrical shell structure, which is much smaller than the radius a of the cylindrical shell structure measured to the mid surface of the cylindrical shell. Hence, the mathematical representation of the thin shell assumption in the region of interest, that is, in the region of the solid material of the shell, mathematically describes the thin shell assumption. Since in the region of interest, that is the region of the solid material of the shell, the radial coordinate r of the cylindrical coordinate system of reference axis selected for the membrane analysis ranges over a small range from a minus t by 2 to a plus t by 2, And since T, the thickness of the cylindrical shell structure in case of a thin shell is much smaller than the radius A of the cylindrical shell structure, the mathematical representation is sufficiently accurate and realistic in depicting the thin shell assumption. As far as the second simplifying assumption, that is assumption number 2, which is based on the idealization that the external forces or external loads are axisymmetric or act axisymmetrically with respect to the longitudinal axis of the cylindrical shell, the most direct mathematical implication of the assumption number 2 of axisymmetric loading is that P theta, that is the circumferential or tangential load, must be equal to 0 to satisfy axisymmetry. Additional implications of the assumption number 2, that is the assumption of axisymmetric external loading, will be discussed in the next slide in continuation of the membrane solution of thin cylindrical shells subjected to axisymmetric loading based on the membrane theory of thin cylindrical shells. Continuing with the membrane analysis of thin cylindrical shells based on the membrane theory of cylindrical shells, realizing that the statical equilibrium equations that were derived from the considerations of statical equilibrium of the differential thin cylindrical shell element based on the assumption of a thin shell does not result in a determinate solution for the unknown internal in-plane or membrane actions nx and theta, nx theta or n theta x, since nx theta and n theta x are complementary in-plane or membrane shear forces and therefore equal to each other, the solution of one will result in the solution of the other. Also noting that the membrane solution of the unknown internal in-plane or membrane actions nx n theta and nx theta is statically indeterminate because of the variational terms emerged in the statical equilibrium equations derived in the previous slide based on the considerations of the statical equilibrium of the differential thin cylindrical shell element. Since the variational terms, that is, the variational components del by del x and del by del theta of the unknown internal in-plane or membrane actions nx, n theta and nx theta result in a differential equation that is based on the statical equilibrium of the differential thin cylindrical shell element, and in general the differential equation based on the statical equilibrium considerations of the differential thin cylindrical shell element may be a partial differential equation as suggested by the statical equilibrium equations that were derived for the differential thin cylindrical shell element after the application of the thin shell assumption in the previous slide. Hence, recall that we had to apply another simplifying assumption or idealization, that was assumption number 2, the assumption of axisymmetric loading, that is, the assumption that the external loading or external forces acting on the differential thin cylindrical shell element are axisymmetric or act symmetrically with respect to the longitudinal x-axis of the cylindrical shell structure. Let us now proceed to the membrane solution of the thin cylindrical shell by applying the assumption number 2, that is the assumption of axisymmetric loading, and the exercise of deriving the membrane solution, that is the solution of the unknown internal in-plane or membrane actions nx, n theta and nx theta in a differential thin cylindrical shell element implementing the assumption of axisymmetric loading will be termed as membrane analysis of thin cylindrical shells subjected to axisymmetric loading. Since the statical equilibrium equations that were derived in the earlier slide based on the statical equilibrium of a differential thin cylindrical shell element based on the assumption of thin shells only resulted in partial differential equations. Due to the variational terms or the variational components del by del x or del by del theta of the in-plane or membrane actions nx and theta and nx theta, and the integration of the partial differential equations that were derived in the earlier slide based on the statical equilibrium considerations and the thin shell assumption will result in unknown constants of integration, say C naught, C0, that is C1, C2, etc. Each of these unknown constants of integration that emerge from the integration of the partial differential equations derived as from the statical equilibrium considerations of the differential thin cylindrical shell element in one of the earlier slides present an additional unknown. The assumption number 2 is therefore not only necessary but also relevant to complete the membrane solution of the thin cylindrical shells, that is, the membrane analysis of thin cylindrical shells in order to solve for the unknown internal in-plane or membrane actions nx and theta and nx theta. It is worthwhile to mention here that assumption number 2, that is the assumption of axisymmetric loading, based on the idealization that the external loads act on the thin cylindrical shell symmetrically with respect to the longitudinal axis of the cylindrical shell structures. And the assumption of axisymmetric loading is not only realistic and valid for a number of practical cylindrical shell structures that are commonly implemented in the industry, but also results in considerable simplification in the membrane analysis of thin cylindrical shells. Based on physical reasoning or engineering intuition, the assumption number 2 of axisymmetric loading, that is the axisymmetry of external loads acting on the differential thin cylindrical shell element implies that the tangential or the circumferential loads must be zero. Mathematically, the external tangential or circumferential load p theta must be zero to satisfy the assumption of axisymmetric loading, since tangential or circumferential load p theta violates axisymmetry. Further, the only external loads or the external forces acting on the differential thin cylindrical shell element that can assume a non-zero value are the axial or the longitudinal external load Px, which in general may be a function of the cylindrical coordinate x and r, or the radial external load PR, which also in general can be a function of x and r. For the condition of axisymmetric loading to be valid, that is, for the simplifying assumption of axisymmetric loading on the differential thin cylindrical shell element to be acceptable and reasonable, the only finite or non-zero external loads that can act on the differential thin cylindrical shell element are the axial load Px and the radial load PR. It may be mentioned that the assumption of axisymmetric loading, that is, the assumption that the external loads acting on the thin cylindrical shell are symmetrical with respect to the longitudinal x-axis of the cylindrical shell structure is not too restrictive and is quite general, since number of practical cylindrical shell structures that are constructed in the industry are axisymmetrically loaded or subjected to axisymmetric loading, such as the cylindrical water tanks and the cylindrical pressure vessels cited as examples of practical cylindrical shell structures. Assumption number 2, based on the simplifying idealization that the external loads acting on the thin cylindrical shell are axisymmetric and act on an axisymmetric structure, that is, a structure that is symmetrical by geometry or symmetrical in geometry about the same axis of symmetry, that is the longitudinal x-axis, about which the external forces or the external loads act symmetrically, implies in mathematical terms that there is no variation of any quantity in the tangential or circumferential direction theta. The hypothesis of no variation of any physical quantity about or along the tangential or circumferential coordinate theta, expressed mathematically by equation number 7, is based on the physical reasoning that the thin cylindrical shell structure is an axisymmetric structure by geometry and is subjected to axisymmetric loading by virtue of assumption number 2, and the axisymmetry of both the geometry of the cylindrical shell structure as well as the axisymmetry of the externally applied loads intuitively should preclude or disallow any variation of any physical quantity along the tangential or the circumferential direction theta in terms of the cylindrical coordinate axis theta of the cylindrical frame of reference selected for the membrane analysis of the cylindrical shell structure. Since any variation of any physical quantity along the cylindrical tangential or circumferential coordinate theta will violate axisymmetry of the physical response or the structural behavior of the cylindrical shell that is predicted to behave axisymmetrically due to the axisymmetry of the geometry of the cylindrical shell structure as well as the axisymmetry of the external loads. Equation 7 that mathematically depicts the axisymmetry of the structural behavior or the structural response of the differential thin cylindrical shell element subjected to axisymmetric loading implies that axisymmetry of the structural response that is intuitively predicted or visualized for any axisymmetric structure such as a cylindrical shell structure subjected to axisymmetric loading necessarily requires that there is no variation of any physical quantity in the tangential or the circumferential direction theta. Substituting equation number 7 into equation 7a presented in the previous slide, that is the force equilibrium equation or the statical equilibrium equation for the force in the longitudinal or axial direction x results in equation number 8. Since all the variational terms that involve variation of any physical quantity in the tangential or circumferential direction theta are substituted or specified as 0, as mathematically derived in equation number 7. Hence, substituting 0 value of the variational terms involving variation of any physical quantity with respect to the tangential or circumferential direction theta as 0, the statical force equilibrium equation in the x direction results in equation number 8, cancelling the like terms with opposite signs. The equation number 8 can be simplified further to an ordinary differential equation as opposed to the partial differential equation that was earlier presented or derived in the previous slide. And as one may intuitively understand that an ordinary differential equation is much simpler to handle and solve than a partial differential equation. Specifically, question number 8, after simplification and rearrangement of terms and noting that the partial derivative of the in-plane or membrane action Nx may be considered as the full derivative, since the in-plane membrane action Nx does not vary along the radial coordinate r or the circumferential coordinate theta, and also noting that the differential quantity dx, that is the differential dimension of the differential thin cylindrical shell element presented in the figure in one of the earlier slides, can be cancelled from both sides, that is left hand side and the right hand side of the equation. The substitution of the mathematical conditions represented by equation number 7 based on the assumption number 2 of axisymmetry into the statical force equilibrium equation for the differential thin cylindrical shell element results in a simple ordinary first order differential equation that is represented by equation number 9 and circumscribed in the green rectangle, since equation number 9 seems to be one of the final equations of the membrane solution for the differential thin cylindrical shell element exhibited in the figure in one of the earlier slides. Based on the application of the statical equilibrium equations as well as the two simplifying assumptions of thin shell and axisymmetric loading. It may be noted here that equation number 9, that is the first order ordinary differential equation, may be replaced or considered equivalently with the algebraic equation involving an indefinite integral, as in case of any first order ordinary differential equation, that may be considered interchangeably, or maybe interchanged or substituted or replaced by an algebraic equation with an indefinite integral, wherein the algebraic equation is obtained by integrating the first order ordinary differential equation, for example equation number 9, that may be integrated to arrive at the algebraic equation number 9, numbered as using the same number 9, since the two equations are equivalent or interchangeable. However, the algebraic equation number 9 with the indefinite integral, as in case of any ordinary first order differential equation, results or consists of an unknown constant of integration that is denoted as C naught in the algebraic equation number 9 based on the indefinite integral. Further, as far as the other in-plane or membrane actions are concerned, apart from the unknown internal or membrane axial force Nx, we also need to determine the unknown internal in-plane axial force n theta, as well as one of the two unknown internal in-plane shear forces nx theta or n theta x, which are complementary in-plane or membrane shear forces and therefore equal to each other, and thus only one needs to be determined. The solution of one results in the solution of the other. The assumption of the thin shell implies that the axial or longitudinal external load Px, which in general may be a function of the longitudinal or axial coordinate x as well as the radial coordinate r in the selected choice of the cylindrical coordinate system of reference axis, will only be a function of the longitudinal or axial coordinate axis x Similarly, the external radial load PR, which in general for a general differential thin cylindrical element can be a function of the longitudinal axis x and the radial coordinate r of the selected choice of the cylindrical coordinate axis. Will be a function of only the longitudinal or axial coordinate axis x in the selected choice of the cylindrical coordinate system of reference axis. Since the assumption of thin shell implies that the solid material or the region of interest in the solid continuum of the thin cylindrical shell lies in a very small range of the radial coordinate r, that is between a minus t by 2 to a plus t by 2, where t, the thickness of the thin cylindrical shell, is much smaller than the radius of curvature of the thin cylindrical shell. And hence, due to the small range of the radial coordinate r, that is relevant physically, or that is physically valid in case of a thin cylindrical shell, from the point of view of solid mechanics, as the solid material is confined only in the thin cylindrical shell in a small range of the radial coordinate represented by this inequality. Hence, the thin shell assumption, mathematically depicted by this inequality, implies that the external loads, that is the external axial or longitudinal load Px and the external radial load Pr, are functions of only x. That is, the external axial or longitudinal load Px and the external radial load Pr are not functions of r, and therefore are functions of only the longitudinal or axial coordinate x. The assumption of axisymmetry results in considerable simplification of the statical force equilibrium equations derived in the earlier slides based on the assumption of thin shell alone, since axisymmetry, that is axisymmetry of not only external loading but also axisymmetry of the structure in geometry, as in case of the cylindrical shell structure, implies that the in-plane or membrane shear forces nx theta and n theta x have to both vanish to satisfy axisymmetry, since by their very nature the in-plane membrane shear forces nx theta and n theta x violate axisymmetry, as can be visualized by the figure presented in one of the earlier slides for the differential thin cylindrical shell element with the general state of internal actions presented in an earlier slide. The simplification resulting from the vanishing of the in-plane or membrane shear forces nx theta or n theta x as represented mathematically by equation 7a, when substituted into the statical force equilibrium equation in the longitudinal x direction x derived in one of the earlier slides, results in a much simpler equation for the solution of the in-plane or membrane axial force Nx, which may be expressed as the first order ordinary differential equation 9 circumscribed by the green rectangle, or an algebraic equation with an indefinite integral also numbered as equation number 9, since the two equations, that is equation number 9 that presents a first order ordinary differential equation and equation number 9 that presents an algebraic equation with an indefinite integral, are equivalent and interchangeable. Continuing the membrane analysis of a thin cylindrical shell based on the membrane theory of thin cylindrical shells, recall that the application of the assumption number 2, that is the second assumption, which idealizes the thin cylindrical shell to be subjected to axisymmetric loading, that is external loading which is symmetrical with respect to the longitudinal axis of the cylinder or the cylindrical shell, and thus is devoid of any tangential or circumferential external load, since tangential or circumferential external load p theta would violate axisymmetry, and thus the external tangential or circumferential load p theta must be 0 to satisfy the requirement of axisymmetric loading. Further, recall that the assumption of axisymmetry, that is the assumption of axisymmetric loading acting on an axisymmetric structure such as a cylindrical shell structure that is symmetrical in geometry with respect to the longitudinal x-axis of the cylindrical shell would also result in the vanishing or reduction of the in plane or membrane shear forces nx theta and n theta x as expressed by equation 7a in the previous slide. Further, the axisymmetric conditions that are enforced or applied by the assumption number 2, that is the assumption of axisymmetric loading, or simply referred to as the assumption of axisymmetry, would also result in the vanishing of any variational term with respect to the tangential or circumferential coordinate theta as expressed by equation number 7 in the previous slide, which implies that there is no variation in any physical quantity with respect to the tangential or circumferential coordinate theta in order to satisfy the axisymmetric conditions or axisymmetry in case of a thin cylindrical shell subjected to axisymmetric loading. Substitution of equation 7 and equation 7a, that is, substituting the zero values of the variational term del by del theta for all physical quantities from equation 7, and substituting the zero values of the internal in plane or membrane shear forces nx theta and n theta x from equation number 7a into the force equilibrium equation in the x direction or the longitudinal x direction, results in an ordinary first order differential equation that relates the internal in plane axial force nx to the external load Px acting on the differential thin cylindrical shell element subjected to axisymmetric loading. The simplified state of internal actions that will exist or that can exist in the differential thin cylindrical shell element that is subjected to axisymmetric loading based on the virtue of the axisymmetry is shown in the figure presented in the current slide that illustrates the simplified state of internal actions that can exist in a differential thin cylindrical shell element subjected to axisymmetric loading in order to satisfy the axisymmetric conditions. As one can note from the figure, all the variational terms with respect to the tangential or circumferential coordinate theta are absent or have vanished since the variational terms with respect to the tangential or circumferential coordinate theta by their very nature violate axisymmetry. Similarly, the internal in-plane or membrane shear forces nx theta and n theta x are also absent from this revised figure of the state of internal actions in a differential thin cylindrical shell element, which is also free from the internal in-plane or membrane shear forces nx theta and n theta x, since non-zero or finite values of the internal in-plane shear forces nx theta and n theta x by their very nature would violate axisymmetry and thus cannot exist under axisymmetric conditions that are enforced by the assumption of axisymmetry. Proceeding or continuing with the membrane solution for the thin cylindrical shell subjected to axisymmetric loading based on the assumption of thin shells as well as axisymmetric loading and therefore axisymmetry or existence of axisymmetric conditions in the differential thin cylindrical shell element, applying the statical equilibrium equation for the force equilibrium in the tangential or circumferential direction theta, that is sigma f theta equal to 0, and substituting the zero values of the variational terms with respect to theta from equation number 7 presented in the previous slide, as well as substituting the zero values of the in-plane or membrane shear forces nx theta and n theta x from equation number 7a, also presented in the previous slide, into the statical force equilibrium equation in the tangential or circumferential direction theta, results in an equality between n theta and itself as expressed by equation number 10, which at the first appearance does not seem to offer any additional useful information, since equation number 10 or the equality presented by equation number 10 simply implies the axisymmetry of the structural behavior of the thin cylindrical shell subjected to axisymmetric loading. However, a closer look at the derivation of equation number 10, that is examining the mathematical formulations that are implemented in the derivation of equation number 10, imply the mathematical verification of the assumption of axisymmetry. In other words, equation number 10 mathematically verifies that the internal in-plane or membrane axial force n theta is constant along the tangential or the circumferential coordinate theta, and therefore equation number 10 serves as a mathematical verification of the physical behavior that one would intuitively predict in case of axisymmetry or axisymmetric conditions. In a sense, equation number 10 mathematically confirms the premise of axisymmetry by verifying that none of the physical quantities, including the internal in-plane axial force n theta, vary along the tangential or circumferential coordinate theta. Proceeding to the third statical force equilibrium equation, that is the application of the statical force equilibrium equation in the radial r direction, and substituting that information provided by the equation 7 and equation 7a from the previous slide, that is substituting the zero values of the variational terms with respect to the tangential or circumferential coordinate theta, as well as the zero values of the internal in-plane shear forces nx theta and n theta x from equation 7 and equation 7a respectively, presented in the previous slide, into the statical force equilibrium equation in the radial r direction, results in a relationship between the internal in-plane axial force in the tangential direction or the circumferential theta direction and the external load acting in the radial direction as depicted in this figure for the differential thin cylindrical shell element with axisymmetric conditions. Hence, the substitution of equations 7 and 7a into the statical force equilibrium equation in the radial direction results in a relationship for the tangential axial force n theta x measured or specified per unit length with the external radial load PR, and in general both the external radial load PR as well as the internal tangential axial force n theta can be a function of x only due to reasons that were described in the previous slides. It is worthwhile to note here that the tangential axial force n theta x is more commonly termed as the hoop force, and thus equation 11 expresses a relationship or mathematical formulation for the hoop force per unit length, that is the tangential axial force per unit length, n theta x, in terms of only the external radial load PR, which is independent of any other internal action. Equation 11 is one of the most fundamental and useful mathematical formulations resulting from the membrane analysis of thin cylindrical shell subjected to axisymmetric loading, since equation 11 provides the relationship for calculating the hoop force per unit length or the tangential axial force per unit length n theta x in a thin cylindrical shell subjected to axisymmetric loading independently of any other internal action. In other words, the relationship expressed by equation number 11 for the hoop force per unit length n theta x is independent of any other internal action and is therefore decoupled from all other statical equilibrium equations or the mathematical formulations resulting thereof. Continuing further, examining the simplified state of internal actions as depicted by the figure or a differential thin cylindrical shell element presented in the current slide, the state of internal actions that results in the differential thin cylindrical shell element after the application of the assumption number 1, that is the assumption of thin shell, and assumption number 2, that is the assumption of axisymmetry, based on the statical equilibrium equations, consists of only two internal actions, which are the in-plane axial force in the longitudinal x direction, that is denoted as nx, and the in-plane axial force in the tangential or circumferential direction theta, denoted as n theta, of which only the in-plane axial force in the longitudinal x direction, denoted as nx, has a variational term. Since variation of any physical quantity in the tangential or circumferential direction theta is precluded or not permitted by the assumption of axisymmetry. In other words, since axisymmetry or the existence of axisymmetric conditions in the differential thin cylindrical shell element exhibited in the present figure does not allow any variation in the tangential or circumferential direction theta. Only variation that can exist is in the internal in-plane axial force acting in the longitudinal x direction, denoted as nx. Hence, summarizing the solution of the membrane actions determined by the application of the statical equilibrium equations by implementing the thin shell assumption as well as the axisymmetry assumption, the membrane solution of the thin cylindrical shell subjected to axisymmetric loading can be interpreted as follows. A, on the application of the two assumptions, that is assumption 1 and assumption 2, wherein assumption 1 is the thin shell assumption while assumption 2 is the assumption of axisymmetry or axisymmetric conditions in the thin cylindrical shell, all the statical equilibrium equations, that is the three force equilibrium equations and the three moment equilibrium equations, have been utilized to simplify the state of internal actions in the thin cylindrical shell, and the mathematical formulations resulting from the application of the 6 statical equilibrium equations numbered as capital A, consisting of 3 statical force equilibrium equations and 3 moment equilibrium equations, based on the simplifying assumptions of the thin shell as well as axisymmetry, have resulted in equations 9 presented in the previous slide as the mathematical formulation for the in-plane axial force Nx, and equation 11 presented in the current slide expressing the mathematical formulation for the in-plane axial force n theta in the tangential or circumferential direction theta. However, there is an unknown constant of integration C naught or C0 in equation number 9 presented in the previous slide, that is the mathematical formulation for the in-plane axial force in the longitudinal x direction denoted as Nx presents an unknown constant of integration C0 or C0 as expressed by equation number 9 in the previous slide. Hence, in summary, although we have utilized all the statical equilibrium equations, that is, all the 6 equations that can be formulated based on the considerations of statical equilibrium, and we have implemented or applied all the realistic and rational assumptions that are valid and admissible from the point of view of physical behavior or the mechanics of thin cylindrical shell subjected to axisymmetric loading. There is still one unknown left to be solved in order to complete the membrane solution, which is the unknown constant of integration C0 that is to be determined for the indefinite integral presented by the relationship or mathematical formulation for the in-plane axial force Nx in the previous slide. Hence, in conclusion, it appears that after all the simplifying assumptions and the subsequent simplifications that have been incorporated in the membrane analysis and exhausting or utilizing all the 6 equations that are available from the consideration of statical force and statical moment equilibrium, there is still one unknown that is left to be solved, and hence one can conclude the present status of the membrane solution is statically indeterminate even after the application of the 2 realistic and rational assumptions that can be applied in a reasonable simplification, and after utilizing all the 6 statical equilibrium equations, the membrane solution of a thin cylindrical shell subjected to axisymmetric loading remains statically indeterminate simply because of the one unknown constant of integration C naught that has emerged from the integration of the differential equation that governs the in-plane axial force Nx as presented by equation number 9 in the previous slide. Therefore, it appears that the membrane solution of a thin cylindrical shell subjected to axisymmetric loading is statically indeterminate, and thus we need to resort to kinematics or compatibility of displacements as in case of any statically indeterminate problem in structural analysis.